All right, so let's look at how does this help us. Essentially, we're going to use our old techniques with Laplace transforms, and then just apply our new Dirac delta transform that we just barely learned about. So we want to do our Laplace transform of the second derivative plus the Laplace transform of y. Because of linearity properties, we can essentially factor the 4 out. So I want to do the Laplace of the Dirac delta of t minus 2 pi. Okay, and then there's nice lovely conversions for each of those terms. So the second derivative of Laplace is s squared y of s minus s of y of 0 minus y prime of 0 plus, and then we just want the Laplace of y is just y of s. Okay, and then the Laplace of the Dirac delta is 4e to the negative 2 pi s. Alright, and then we can take into account our initial conditions. So y of 0 is 1, so that part right there becomes 1. And then y prime of 0 is 0, so that part becomes 0. So that's s squared y of s minus s plus y of s equals 4e to the negative 2 pi s, which is going to give us s squared y of s plus y of s equals s plus 4e to negative 2 pi s. And I can factor out the y of s. So that's s squared plus 1 equals everything else. And then divide by s squared plus 1. Okay, then we want to do our inverse Laplace on each of these terms. And hopefully we are familiar with some of the translations there. Or e negative 2 pi s over s squared plus 1. Okay, so that is just going to give me y of t. S over s squared plus 1 is cosine t. The other one, let's see, we can bring the 4 out, and that's a form of sine. But with the e to the negative 2 pi s, we're actually dealing with a transformation, and yeah, we're using that same definition from last lesson on unit step. So 4 sine t minus 2 pi, and then the unit step of t minus 2 pi. All right, and we can translate that back. Well, actually, let's have a quick chat about the sign, because the sign we can have a little bit more fun with. So we say sine of t minus 2 pi. If you think back to your trig formulas, your difference of sine function, we can actually simplify that down to sine of t, which means we can translate this y function back into a piecewise function. cosine t plus 4 sine t. And so that would translate into t being greater than 2 pi, which means it's got to be cosine t when we're going from 0 less than or equal to 2 pi. Sorry, I just realized that bottom piece was hanging off the screen there for a second. You're probably thinking I'm crazy here. I have I think I accidentally hit a setting, and it's converting on some of my number 0 it made into a shape. I don't know if that's an insult to me that it converted it to a triangle. I don't know what that's all about, but anyways. Okay, so the nice part about this one is it's kind of the same question. The only thing that's really changed is one of our initial conditions, which actually simplifies part of the process. But if you recall, we did the Laplace of each of these terms, and so I'll kind of get to the point where the process changes on us. Sorry, that's an equals. Okay, so then I'm going to write out that step for the Laplace transforms for all of those. So that's s squared y of s minus sy of 0 minus y prime of 0 plus y of s equals 4, and then the rest of that piece that we just did. So 4e to the negative 2 pi s. Sorry, s is an exponent. Okay, so what's changed about this one is this time that part is 0 and that part is 0. So that just means we have s squared y of s plus y of s equal to 4e to the negative 2 pi s. So if I factor out the y squared again, so y of s is equal to 4e negative 2 pi s over s squared plus 1. Alright, so when I do the inverse Laplace on that term, right, I just end up getting y of t is equal to 4 sine of t minus 2 pi, and a unit step of t minus 2 pi. And remember that sine of t minus 2 pi is equivalent to sine of t. So that means our y function is equal to 4 sine t when t is greater than 2 pi, so greater than or equal to 2 pi, and otherwise what does it equal? It equals 0. So very similar to the one we just did, we just take out that cosine element.